Andromeda.
They're streaming live.
But maybe they should.
We are get there.
The JPEG.
Says check.
No, I don't know.
I've never had issues.
Cool.
So,
Yep.
okay.
We are live. Hi, everyone. One moment while I send a link.
Are we live right now?
Yep.
Oh,
You can say
hi
hi.
everybody. Welcome to the Vesuvius Challenge office hours. It's a special moment. We have most of the full-time team members present here in Palo Alto. And I think while Stephen's getting set up, I'll kill some time. I think we wanted to sort of provide like a little introduction to the project overall for people who are a little bit new, and maybe give some updates on some of the recent progress that's been made, and talk about whatever you want to talk about. So prepare your questions, put them in the YouTube chat. Is that the right place to put them?
It is, and I will also put in that if you are a participant and you have something you want to show that you're working on, or you want to hop on and get on voice, say hello, have a question, I'm going to put an email in the chat. You can send us a message and I'll send you a link so you can actually join the Zoom call.
Should we do it with quick intros so people know who everybody is? Is that a good idea? Yeah. So I'm Nat. I was the instigator of the project, and these guys are doing all the actual work. So you want to go next?
Yeah. Hello, I'm Julian. I started last year as a hobby, and then Nat employed me for doing development auto segmentation.
My name's David. I'm one of the
Say your Discord name so that people.
Oh yeah, so I'm Rifi at Discord.
My name's David. The username djosie. I'm one of the segmenters, and recently I've been mostly working on Scroll Tree along with some other smaller projects.
I'm Luke, or Luke Boy, on the Discord. With Julian and Yusuf, I'm one of the grand prize co-winners from last year. These days, I mostly work with Nat on the investment side of things, but I help out with the scrolls here and there. Right now, I'm doing lots of ink detection work.
Hey, I'm Giorgio. On Discord, I'm Jordi, and I recently joined the team to work on auto segmentation.
I'm Harry Sullivan on the server, and my name is Ben, and I'm also on the segmentation team.
I'm Steven. I've been working on scrolls for a long time, and I'm project lead now for Vesuvius Challenge.
How many years have you been working on the scrolls?
I have been working on scrolls. I've been working on these scrolls for 7 years.
Yeah. So Stephen's work is what
did
made
some other
all
scroll work 3 years before that.
Okay, so a decade of work. So Stephen's work is why we're all here. He laid the groundwork for everything.
And I'm very excited to be here now. This is like beyond wildest dreams of what we thought we'd be doing.
Cool.
So yeah, so we're together this week. We can share a bit of what we're up to. So we are working on some new resources for the community. So we're going to have some updated documentation and some tools that hopefully make the data a little bit more accessible. One really nice problem we have is that we launched this last year and have had all this amazing progress from the community and those of you watching. And so there's a ton of new information that's been generated, and we have our hands full now to communicate more effectively where we are, what's been done, what the challenges are today, how they're going, and where everyone else can contribute. So we have the team together this week to work on that. Hopefully soon you'll see more of that from us. While we're here, we can each talk a little bit about what we're up to. I have some pictures we can show of some of the scroll data, and then we'll take questions and just see how it goes. Anyone want to share what they're up to? Should we go around again and just introduce
Why don't you
ourselves?
do the photos first? I think that'll be.
Let's do it.
No, we can do it.
Are any of you watching the chat?
Yeah,
I'm
there's
Discord
no
right
questions.
now. Yeah, no questions.
The YouTube chat?
No questions yet.
Cool. I have it open, but I won't if I'm showing things. All right. on sharing, and hopefully this comes through. So I thought it'd be fun to show that all of this information, yeah, exists somewhere and you could find it. And here it's a little bit more consolidated, and we'll work on making this more consolidated on, for example, the website. But I thought it'd be fun to show, now that we've really actually dug in a little bit to all the scrolls we have, basically what they look like and where the challenges are for each of them, because it turns out they're each their own little special butterflies with interesting personalities we're getting to know. So this is the one we all know the best, and I will be just kind of going through this. Anyone else can speak up to weigh in on anything we're looking at, because you have a lot of experts in the room, and then let me know if we get questions. This is the scroll we all know the best. This is Pierre Paris 4, aka Scroll 1. These are photographs of the exterior of the scroll from each side. It's pretty beautiful or ugly, depending on how you look at it. I think especially this end view on the top right is pretty amazing. So this is a model of just the outside of the scroll. This is the product of doing photogrammetry on the scroll. And for our purposes right now, it's just sort of fun to look at. This is useful technically because we use this model to 3D print a case that form fits the scroll, and that's necessary to stand the scroll up vertically and scan it. So that's a whole process of its own so that we can get the data that we ultimately work with. And that data looks like this. So many of you are familiar with this. This is the inside of Scroll 1, just an overview. The outside here, this thick band is the inner lining wall of the plastic case that's been 3D printed. So that's a nylon material that sort of form fits the case, and then there's a thin layer in between that and the actual scroll that is a Teflon relic wrap material that sort of gives a little hammock between the scroll and the hard plastic shell. The case is in two halves, so here at the bottom and a little bit maybe at the top, you can see where those halves join together. So we lay the scroll in one half and set the other one on top, and then we can pick up the assembly and set it in the scanner. And this in the middle is the papyrus of the scroll. So more people now have spent many hours looking at this. A while ago, myself and a couple other people at the university had stared at this more than anyone else, but I don't think that's true anymore. So some of us in the room and on the call have spent many, many hours understanding this material. From this outside view, you can see it's sort of spiral shaped but quite deformed. So the scrolls were crushed at the same time they were burned. That is one of our challenges in segmentation that we can talk about today. But yeah, let's zoom in because there's more details here that are interesting. Here's kind of the inside of the scroll core, and this is pretty segmentable. Yes. So this, believe it or not, is traceable. We have a team that's sitting here that has developed the ability with software and in building a lot of expertise to trace this spiral of papyrus and to capture that shape. And you can actually see papyrus fibers here, so I don't know how clear it is in just a single cross section, but what we're looking at is a papyrus sheet that has horizontal fibers and vertical fibers. And the horizontal fibers you can think of as kind of going around the spiral, and the vertical fibers poke in and out of the screen. So sometimes you'll see sort of dots that are vertical fibers that if we were to traverse the length of the scroll, you'd be able to follow those into or out of the screen. This is a pretty nice region. It's a bit of a mess, but it's a mess that we can handle. There are other regions that are much less kind. So here's near the outside of the scroll where a bunch of these papyrus layers are really tightly compressed. This sort of obviously makes it a lot more difficult to trace them, certainly manually, but also for some automated tools we're working on. This is where we have quite a challenge. Anyone have any opining to add to these compressed regions?
So
I think we can segment this. If you spend a lot of time, you can make a small segment with it, but it's just hard to scale right now.
Also, maybe it's the view that we have right now. So if you have a different angle of view of this region, it might look a lot simpler.
Do you mean if you rotated kind of your slice direction to look more parallel to the sheet?
Exactly.
Yeah, that's something that really bumped my confidence in this set of methods, or just the ability to segment this in general. If you look at this view, like Julian's saying, it just looks basically impossible. Like if this slice was all you had, it's just a big impenetrable blob. But it turns out if you rotate the way you're slicing it, there's a lot of structure here that's not so evident in this view, and actually you'll see the papyrus fibers in the sheet, which we'll look at in a moment.
And I would like to add that maybe locally, looking just at the single voxels, we don't know basically what's happening around. But since we know that every papyrus sheet has a thickness,
Yep.
if we look more far away, basically with more global context, we may be able to follow the sheet and separate them.
Yeah, so would an example here be kind of on the top left, you can see these layers entering this region. So if you look only here, you would have no idea what's going on. But you know that there are, like you could count these layers, and maybe there are 9 or 10. You could take your time to get a more accurate count. And you know then a lot more about what's going on here, basically. Yeah. Yeah, so globally there's a ton of information. One of the challenges of advancing segmentation, I think, is going to be to combine the local image information with this sort of global constraints that you get from the material.
We have a question about that region. Question is from Jared. Do we expect much improvement in segmenting compressed regions if we were to scan at a higher resolution? Or have we reached the point of diminishing returns in that regard?
Let's discuss. I'll share again and pause to check email. What do you all think?
Good question. We haven't explored compressed 3.24 resolution.
So in my opinion, it depends what do we intend for compressed, because right now we have a fixed resolution. So basically, you can imagine two sheets touching, and if there is some air gap in the middle, maybe at this resolution we are not able to see them, to see it, but with higher resolution we can. Another thing is if really the sheets are touching. So if really the sheets are touching and there is no hair, then no matter our resolution, I mean, what the resolution, we should go really to, I think, nanometers or even lower to see the separation between molecules. So it depends. For sure, I think with a higher resolution, we may be able to resolve a lot of conflicts that right now we can't, but probably with really pressed sheets, then it wouldn't be enough, and we should find another way to solve it. So it's basically that's it. And this is what also we are trying to do with the cubes that Ben and the segmentation team are making, because basically we are inserting information, local information, by separating the layers, basically, that we cannot simply extrapolate from the data that we have right now. So I don't know if it was clear, or maybe I should go.
I think that makes sense. That's my guess as well, is I think there is more to be gained from higher resolution.
Yeah.
If you go back in time to 15 years ago, this scroll was scanned at 25 microns or so, and I don't have those images in front of me, but you would see that basically the whole thing looked like what we would now call a compressed region. It turns out if you improve from 25 to 8 micron resolution, a lot of what looked like a big compressed blob now looks really nice. And then now there's still some tricky regions that look like big compressed blob. But I'm optimistic. I don't think we've hit diminishing returns there yet.
And
There are challenges to scanning the whole thing at high resolution, but we're working on that too.
That 8 micron is effectively 40 microns.
So there is
There's some nice in here.
We say resolution speaking of the voxel size or the pixel dimensions of this, and that is not necessarily the same as the actual captured level of information. So inherent in the CT scan, the voxel size is sort of fixed, but based on the physics of the scan itself and the object and scattering that's going on, you get effectively blurring and noise that are introduced. So when we say 8 micron, that does not necessarily mean that the scan would resolve a physical feature that is 8 microns big. It might be more like 20 or 40. But it certainly improves as the voxel size comes down, the effective resolution does as well.
So Stephen, what do you think would be the highest resolution we could reach the technology we have right now?
With the technology we have right now, we can scan full scrolls, it's annoying because it generates an enormous amount of data that's, and then we introduce other problems for ourselves. But we could scan this entire scroll at 3 microns, is about the best it could be done right now. One thing the team's been working on that we haven't released details of yet is we are working on more data sets. So we have been doing some scanning, and there is some of that data that we'll be able to answer some of these questions because we have full scroll data, not for an entire scroll, but for significantly large chunks of scroll that will directly compare 8 and 3 at least. So pretty soon we can start to answer these questions.
And also this new scan, I think there was also something done with like the 8 micrometer scan. Maybe we have like a higher flux, but I think there's less noise in that scan as well. So even the 8 micrometer higher resolution.
And the requirements for auto segmentation and the requirements for ink detection may be greater.
Now, thanks.
We have had, let's see, I've sent a link to a couple of people. Has no one joined yet? Jared's on the call. Feel free to speak up anytime, Jared. And James may be joining us as well. For now, we can just proceed. Will we hear it if Jared speaks up? We have our own audio turned off so that we're not.
Can you guys hear me?
Yeah, there we go. Hi, Jared.
Nice. Nice to meet you all.
Yeah, thanks for joining. Do you have anything you want to ask or show, or you want to just hang out, or how's it going?
No, I'm just enjoying the presentation right now, but I'm sure I'll have more questions for you shortly.
Great, thank you so much for joining us.
No worries.
We can hear you loud and clear. All right, we'll just proceed then. Cool, so yeah, a lot of us have looked at this before, but this is another visualization of the same data we were looking at just to show what this data looks like after we actually do the segmentation and flattening process. So this is a sheet made by the segmentation team, which is in the room. Anybody know who made this? Want to claim it?
If that's a scroll one segment, it's been a while since I looked at them. Kind of looks like 1619.
I wonder if we, I don't know.
Yeah.
They were all quite collaborative.
Cool. Yeah, so a team effort. This view probably doesn't show much, so really I wanted to just zoom in and show this type of image, which probably most people on the call have seen for scroll one. Really the point here is we're going to show the other scrolls and compare this to those to illustrate that they have special, unique personalities each. So this is a texture image of scroll one, and you can see the papyrus fibers clearly. There's vertical ones and horizontal ones. We know based on this scholarly information about how papyrus was made and used that the horizontal fibers typically were on the top of the sheet where the writing would occur. That becomes the inside face when it's rolled up on these scrolls. And usually in Herculaneum, there's only writing on that side. Not always, but I think at least 95% of the time. There's only writing on that recto side with these horizontal fibers. There's all kinds of features going on. So we have little cracks, there's bright spots. Sometimes the bright spots follow patterns or structures, so they'll follow papyrus fibers. I don't personally know what that is. We'll see it again.
Aren't they mineral accretions in the plant as it grew?
That seems very possible. I would believe that readily. I think I show later there are cases where they follow other patterns that are much more interesting, which is to say that sometimes we see patterns like that where there is text. And that we don't have as much of an explanation for, but yeah, all kinds of stuff going on. Sometimes it is actually ink, and we now know this. So this is one of the really nice results of last year as we discovered, or Casey found this crackle pie inside scroll one. So you can see this sort of textural difference where this pie character in the image is not brighter, but it does not necessarily much brighter than the surrounding papyrus, but it has this cracked mud sort of pattern to it. And this was our foot in the door with scroll one. So once we found this, actually some additional time passed, but eventually we started training models on this. And the first person to really do that successfully, Luke, is also in the room. And yeah, it turns out if you label this as ink and train a model, you can train a model to detect this sort of pattern and start to show ink. And if you rinse and repeat and you grow your data set, you can achieve what we got last year, which is models that can recover substantial portions of text from inside the scroll. So on the scroll one front, ink detection works or mostly works. It's great. Here's the result of that with some little icons illustrating one measure of legibility for each of these lines. So you'll see that some regions are better than others. We can't read the whole thing yet. There's work to be done even on scroll one to improve the clarity of what we're recovering. But this is really substantial text that we can read. That's very exciting. Now we'll get into the real fun stuff and what we're trying to do this year, which is we want to extend this and read more scrolls. So we've read about 5% of the one scroll. We want to read all of the scrolls. So we'll look at some of those. Here's scroll 2 here at Paris 3, which has been released as long as scroll 1 has. We haven't seen as much from it yet, and you'll see shortly why. Even from the outside, you can tell this one's really big. Well, maybe there's not a scale banana in the figure, but you can take my word for it that this one is about the same length and is much wider than the other scroll. So it's a ton of material. Probably the biggest scroll I have worked with in terms of mass. And here's what the inside looks like. It's a big mess. So there are a few things going on here. One is there's a core in the scan that's missing, and that's actually just an artifact of the scan process. So that doesn't reflect reality on the inside of that scroll. That is the result of a misalignment during this particular scan. So we're missing this central little core, and it does introduce some streaking artifacts into the surrounding area. But there's a lot else we can still resolve pretty well. Unfortunately, once we resolve it, it looks like this. So how segmentable is something like this today?
Quite difficult, borderline impossible.
Borderline impossible.
For manually. So,
yeah. Yeah, we can see vague, you could kind of follow the flow here. If you can imagine optical flow or something, there are patterns to the layers. You can imagine tracing them in bulk, sort of developing a flow field, but yeah, it's quite, we're working out for us to trace these individual layers, right?
There are patches that you can do, but they quickly run into areas where the page is bending out of the Z plane and getting really compressed in other regions, so it's hard to follow it continuously for extended length.
So David, but you say borderline impossible because for the amount of data, or imagining an ideal situation where you have an infinite time, would you be able to trace the sheets?
Well, you can trace every sheet.
Yeah.
Yeah, sure.
Okay.
If you have 10,000 hours to just do one little
So,
bit.
Well, actually,
There are-
no, because sometimes it turns out of the set plane and moves back on itself, so you cannot trace the sheet, right?
With open or with infinite time, I can't speak to the different dimensions that you can look at. I've only looked at Z. So there are some regions looking just at the Z plane that I would say with infinite time, it's too compressed.
okay.
But maybe if you're looking at the X or Y or some variant of that, it would.
So if the tools were a bit more flexible in letting you, during segmentation, kind of rotate your viewing plane
Yeah, exactly.
dynamically, follow the contours of this very crumpled mess, it's not all impossible inside scroll 2. Well, here's an example actually of where the sheet has turned and it's rotated so that it's actually somewhat parallel to the way we've sliced it. So over on the left, you see compressed sheets kind of in the same view as earlier, but in this central region, we start to see the cross-hatch pattern of papyrus fibers because we're just slicing right through the middle of a layer instead of cutting it.
Free segmentation. Find some ink.
Yeah.
And then to be clear, all these scroll 2 scans are at 7 microns, right?
These are all 8. Yeah, this is all from the same 8 micron. 7.91 if you wish.
Yeah.
Yeah, you may hear us say 7 or 8. Somebody
The same,
interchangeably.
it's the same number.
Yeah. It's not all impossible. Here's a segment that we have been able to produce. If you zoom in, there is all of this structure, much like in scroll 1. Did we think there might be crackly features in here? Is that true?
Yeah,
Not necessarily in this image.
I'm like,
Scroll?
Oh, I mean, you can see a little bit on the left there, but we don't have to scrutinize it too much. Yeah, right there. Yeah, right there. Yeah. I'm pretty sure there's probably some writing in there that we could find easily if we could segment it better.
And that is coming from the fact that you have spent a lot of time looking at this particular data. I
Yeah,
have seen promising like things going on, right? So-
there's not a ton, not as much as we had with scroll one when that started working. But I've spent maybe 5 hours looking at this in different angles, and I think there's stuff there,
Cool.
as have others.
So if anyone's out there and interested in winning a $60,000 First Letters Prize, take a look in scroll 2. There is maybe hope in there. So we do have some segments that have been released.
Also older ones from last year. The first segments actually came from scroll 2. So yeah.
Yeah. So there may be hope. If you can take a look and find something and start to train a model and get letters to show up, we'd all be very excited and you could win a big prize. So definitely let us know. And we'll be very happy to point you to those segments and other resources.
For sure.
We have another scroll. Let me check, chat check time. We have James on the call. James, hello.
Hello. How are you?
Hi, James.
I'm doing well.
Hi, James.
How are you?
James.
Sorry,
Hi.
managing a few
Yeah.
things.
Yeah, no worries. I do have something to show if you let me share my screen, if now's a good time with the Nepari
Now's-
tooling I've been working
Now's
on.
a great time. We would love to see it. Do I need to give you permissions?
Let's see. Yeah, looks like it worked.
We can see it. That's awesome.
Yes.
What are you looking at?
Yeah. What we're looking at, this is a 512 cube region from scroll 3 with Brunus's ink detection volume. So if I'll just run the connected components and that'll separate all the different labels. So essentially this is like volumetric 3D predictions of where it thinks ink is at. But with the tooling in Nepari, if you select the ink labels, you can hit N and the plane will actually be able to go off axis like this.
Oh,
The cool part about, so you can look, it can actually go at, if you select the data, you can look at any angle, which is really cool. Obviously, it only works for smaller parts, but that might help with some breakthroughs. Also,
so you can kind of query an ink spot and you can basically rotate the plane so you're looking at the crackle if it's there.
Yeah, exactly.
Yeah, that's
And if you
amazing.
hide the label, you can see in this part, it does look like there is crackle there. So you can move through.
Did you say this is
and
scroll
see-
3?
Yeah, this is on scroll 3.
Amazing.
But yeah, you can look at anything. And the other thing is this could become a ink labeling tool, because if you select the ink label with this, you could select the brush and this will allow you to actually draw on the plane like this. So then you can start to refine the labels and get that human in loop machine learning that we were doing in 2D, but do it in 3D. This might have some advantages for looking at areas that aren't already segmented 2D. I think it will be generally easier in 2D to do it, but this is a way to start looking at those 3D volumes ML Ryan and Brunus put together and try and find promising regions. Because the letters are, I think they're quite big. Like this is the 8 micron scan of scroll 3, because that's what ML Ryan and Brunus did it on. So I think you're expecting the letters to be 400 voxels tall or something like this. But if you connect that and then run connected components again on the ink labels layer, you can
How
start
big
to
is
put
the
the chunk size is, I'm using ZARs, so the chunk size can be any size I want it to be.
Okay.
But yeah, you can start to put things together and see if you can find some letters this way, which is pretty cool. I actually built this, or I built on top of Nepari to segment volumetrically to start looking at the harder, denser areas that volume cartographer with its like Z-axis thing won't be able to go into. But I found like, oh, there's these ink ZARs, so I can also put them on here, and then maybe you can find some ink this way. For the volumetric segmentation, I've already made a lot of good documentation on the GitHub repo, which I posted and got a prize last month for, so that was cool. But I thought I'd show off that I was looking at ink detection as well. I also think because the drawing on the plane's a little laggy in the larger one. I think if I hit N, it should be able to reload it, but still in development. But I thought I'd show the direction I was going here.
Yeah.
That's really neat.
It's really exciting.
Yeah.
So you've spent a lot of time looking at these volumetric ink labels. How confident are you that they're accurate?
What do you mean by accurate? Because it definitely
detecting ink. Or do you think it's really noisy and these splotches are just kind of random?
these splotches, I think some of the ones where there's more together could be accurate, and I'm starting to see labels, but the generalization, it's definitely picking up on things that isn't ink as well, for sure. One thing I noticed on scroll 2 and 3 is there's like this really thick layer of crackly looking stuff on the outside that clearly isn't ink because it's nearly as thick as the sheet, and it's like detecting all that is ink because the pattern looks crackly. Like, I think there is some signal in here, but it would have to be manually verified and see if it's starting to make the letter shapes in 3D. And to be honest, I think the majority of this is noise, but it's a lot easier to check these shapes out than going through it completely blind. But yeah.
That one kind of gives you a guide on where regions of interest maybe.
Yeah, exactly.
Maybe there is a path forward here by just like going into Napari or wherever and selecting the patches that you think are proper and then only retrain on those and start kind of
just deleting the ones that seem like noise.
Exactly.
I would like to add that the dark spots that we can see in this layer is basically air. So,
like this.
Yeah.
This
So if you shift, is it possible to shift the layer like more in the orthogonal plane? Yeah.
Like which direction do you want? This or
towards us.
Make it run out of space.
Yeah. Okay. Yeah.
And can you make that plane like a few voxels fixed with an averaged image in there?
Yeah, exactly. Actually, here, over on the left, you can increase the plane thickness so it's taking information. And then you can look, if you line it up with this, I've actually spent probably far too many hours like messing around with this, trying to like find the perfect one, but you can really mess with it. And then if you hide the, not that, but if you hide this, you can really start to mess around it.
Is it just a straight average when you have it thicker that we're looking at?
This is maximum intensity projection, but they have straight average, minimum intensity projection, ISO, like they have lots of options. So you can do all the stuff. Napari had a lot of good features, and then I added even more ones specifically for the scroll, like pretty much this entire right-hand sidebar and all this stuff, and a lot of the keybinds. But you can definitely see there's a lot of crackly looking stuff in this. As you're looking through the scrolls.
And also just at this point, like to shout out to people on the Napari forums who've also helped us. So if any thanks.
They had some PRs that I took some of their functionality from and put it on my own fork because they weren't going to hit the live Napari build for a long time. So especially the smooth labels, that was a big one Ben wanted, and they did the heavy lifting for me, and I made it work for my build as well. So that was nice. Yeah. But yeah, I could do this all day, like staring at this.
This is very
like there has to be something in. Yeah. Thank you. Yeah.
James, no worries if you don't have this handy. Is there any chance you're able to pull up some of the volumetric instance segmentation in the same viewer?
Give me a minute and I can get that up.
Cool. And no worry, you have documented this well elsewhere. So if anyone is interested in that, like there are links to videos that you've made that are great and other resources from the website. So no pressure, but it is very cool. So
I'll be back in like 2 minutes.
Yeah, cool. Yeah, so that actually, I'll go back and share.
Maybe if we're staying on scroll 3 for a moment, I could share the large mesh that I made from scroll 3.
That'd be great.
Okay. Here. So I've produced auto segmentation, a mesh of complete scroll 3, and this is a little bit how it looks like with Cartes. So just loading the object to Cartes. You can see the general shape is well captured, and in the parts where you see the sheets, usually the mesh follows the sheet, but then you can also see that there are obviously places where you have sheet jumping, so like the sheet isn't the same over the complete turn of the scroll.
Are you able to pause and maybe point out one of those?
Yeah, let's maybe go here.
If you don't look too closely, it looks amazing.
Yeah, it looks amazing.
Correct.
But if you go and look closely, for example, here you see this turn, and then the other turn here, and the mesh that just like jumps over. Yeah. And also, sometimes it's also not quite accurate. For example, here you have this turn, but then she just, yeah. So like, you can render this and you probably get a lot of sheet area, but you will have no readable text in the sense of like coherent text, but you should be able to see a lot of letters. So maybe you could render the ink detection volume from Brunis and get some training data. I don't know.
How big is this mesh file?
This is around 400 megabytes.
Okay. Have we rendered it yet, or?
No, not really.
Full?
Because it's a development thing. But there are tools in Taumato. There's a render tool that gives you a live view, and it's really fast. And this tool is actually developed so far ahead now that you can render scroll with it. It renders it in segments, so smaller pieces. So you can just load this and render.
So just to throw light on where we are, more or less. So basically, if we render a mesh like this, we can expect many patches that are well aligned to the surface of the sheet. And as you can see, in all the regions where the line is not following the surface, there will be a jump. So this is why Julian is saying you might be able to read or to track some ink, but if you focus on those patches. So basically, it's actually quite easily detectable on the rendered image where is a right patch and where actually there was a mistake in the segmentation. So I think it could be worth to have a look at this data. And
definitely for ink detection, like not reading, but if you want to have like a working ink detection algorithm, you could probably use this to develop that.
Right. If we could extract accurate patches, then we could just share those as an accurate segmentation.
Yes. Yeah, sure. They are usually a few, like the accurate patches usually are maybe like 3 to 4 letters big. So, yeah.
More than enough to get started.
Yeah, sure.
Yeah.
Sure.
Could you talk just for a minute about the process that leads to making this mesh? It's kind of 2 or so stages, sort of.
So,
and which one of the stages has the issue that is leading to the sheet jumping?
So let's start with like the first
San Diego had the same question.
Yeah.
Cool.
Which is like you have to extract the surface. In Kamato's approach, you extract point clouds on the surface. So here the blue dots are, this is from scroll 3, detect where the surface is.
And this looks like it's primarily recto is the objective, right?
Yes, you only extract the recto side.
Which is the interface of the papyrus.
Yeah, but if you have point cloud like this, lots of points, they have no connection, you have to get connectivity back into this. So point cloud instant segmentation on small patches, these patches are maybe are of this size here, so like a volume of that size, where you extract the patches, and you do this for the whole scroll with overlapping patches as well. And then you have to stitch those back together. And so I think the surface in most cases is detected quite nicely, this as in this example. But then you have to kind of do the connectivity, and there are two main issues. First of all, these instances that these patches, small ones that are created, have a very little training data. So increasing the training set would give a big boost. And then if you have accurate patches we have right now are medium inaccuracy. You have to stitch them, which is a NP hard problem in the general case. Depending on how you look at this problem. And I think that this sheet jumping that we see, the obvious ones, this is from the patch switching, that's the issue. And my general view of this is if you figure out how to do the patch switching correctly, you kind of have an algorithm that almost like at least 50 to 80% of this problem can now know sufficiently well.
Yeah.
Let's see.
If someone was interested in the sheet stitching part of this, is there a particular file we could point them to, or?
I would have to dig it up, but there are files this is condensed into a graph problem. So all these patches are nodes, and then how much they overlap are the edges of the graph. But there is a graph online that you could have a look at on the data server that actually you could go and mess with.
Oh, yeah, like a data file?
Yes.
I meant also like a code file if they wanted to see
yes,
what's going on, whether they might be able to.
So if you go to Tamato, there is a code file, I haven't opened it yet, but it's a random box that solves this problem, like a randombox.py.
Cool.
Yeah. And maybe throw back to scroll 1. So here in this condensed region, you can see still a lot of information can be extracted. This is an older point cloud with like lots of mistakes in it. It's extracting the wrong side of the sheet, but other than that, yeah. So even in a condensed region, you still have information that you can cut.
Nice.
Have we seen the most recent question in the chat? There's a couple.
There's a question about how scroll 4 surface compares, but we will get there. Right?
Okay.
Scroll 4 is on top. And yeah, I think you were just answering Santiago's other question about where things are going wrong.
Okay, yeah. That's it for my.
Yeah, shall we get to scroll 4?
Well, it can
There's
also come
another
in.
question from Tom as well. Go ahead, James.
Well, I could steal the floor again and show the volumetric segmentation labeling in the PARI. I reconfigured the config file for that.
Awesome. Yeah, let's take a look.
Sure. So this is a completed cube. As you can see, when you first load it, all the layers are they're all green usually, and then you can run connected components to separate them. But what you then have to do is go through with the eraser in 3D. So if we take this and say I decide I don't like this part of the label, you can just erase it and get rid of it. And then the point of doing that is to separate all the sheets from each other. So then you can, when you run connected components, you actually get the separate sheets. And then this one's been processed afterwards to push the labels back together, because this one's already done. And then hopefully with this data it's a pretty easy label to give to machine learning software to ideally get some sheets out in different parts. And you can see one thing I've noticed while trying to do this is a lot of the places where the sheets are very dense and together, you sometimes have to follow the sheets up and out of the context of the cube and then find where they're separated later on and then go through and erase it. I'm sure Ben and the other segmenters that have been doing this in Slicer with Napari can mention that as well. Well, I'll go to a cube that isn't done. So like load it. The switching takes a second because I made it auto save every time you switch because I didn't want to accidentally switch and lose all my work. So this is like a cube from a far denser part part of the scroll.
Which scroll is this?
This is scroll 1.
Cool.
Yeah, so you can see on the 2D view, it like goes and gets jumbled and all kinds of weirdness is happening with this one, like going through the label. So I began labeling this, but after there's more work than it looks like, because until you completely separate the sheet, it'll still be the same color. But I think after about 6 hours, like maybe I'll leave this cube for later, because maybe you can get units or other models to give you better initial masks with more or less erroneous connections. But this is when looking at completing auto segmentations, whatever technique will have to be able to deal with regions like this, because this is scroll 1 even, and scroll 2 is pretty much all like this. So yeah, but Empire definitely has the tools to go through there. Like I was making progress, it was just taking forever to do.
Hey James, looking at this data,
Yeah.
I labeled the point clouds, and what I found was really helpful is actually making smaller cubes. So you could, like, I don't know, make 16 cubes out of it that are disconnected, run the connected components at it, and then puzzle together all the pieces that belong together.
Ooh.
So
That's an interesting idea. Actually, I haven't thought of that. Yeah, splitting up even smaller and then rebuilding from that.
Then you just click the ones that are connected together, connect them back together and puzzle it together. So you have like a head start for a lot of parts.
Yeah, that's a really good idea. I'll write that down. Like cut up like CC and then like merge together. Yeah, I could see that providing legitimate speed ups. But yeah, most of the time when you're labeling, you're in a view like this and you're saying, okay, where does is this one sheet? Is this 2 sheets? You're coming through like, okay, looks like, is that connection there one we want? And you're like, okay, I think this is like 1 sheet coming here, and maybe I want to erase it. So you get out the eraser. This is a really comically large eraser, but you might then like disconnect it like this. Then you hit Q and E to go to the next slice and just continue all the way through until the job is done. On the sparser cubes, it's way faster, but it seems like the denser the cube is, the time it takes to label even manually gets exponential, just because there's so many harder regions where you're having to really interpolate like which sheets, which is this 1 sheet, is this 2 sheets, and start looking at it. But hopefully
I'm glad you brought up this data, because here we can clearly see that, as Stephen was saying before, a sheet is made of a wave of fibers. So actually here we can see the fibers that are kind of detaching, and so there is a small air gap in the middle of a single. So this is why it's also hard to detect distances, and this is also why this problem is so hard, because you can see that not only single fibers are like leaving the normal structure of a sheet and touching another one, and this is also not compressed region, but also if you go like in the middle of your cube, like there, more to the, you see that there is this fiber approaching the other distance, and also like whether you start with point clouds or you start with this volumetric data, in the end this is something that when you reach the point that you have to put everything together, this can easily fill up an algorithm that has to perform this job. So in my opinion, this cannot be done without machine learning, and so I think that what you're doing with producing this label is a high value, really of high value. So thank you.
I do think getting these labels and having machine learning be able to create larger sheet labels, so there's less connecting to do in general, and then maybe have ML start to connect them together, because there's just way too many weird edge cases for some deterministic or heuristic to deal with. I think so.
While we have this visual up, I might put my high-level thoughts on sort of framing this, and then anyone can weigh in. Basically, what we're looking at is the frontier of the segmentation problem, or what we've been calling auto segmentation, is sort of twofold. You need some way to make sense of the image data locally. Like you need to go from image data to some sort of representation or structure. And there are different ways to do that. So Julian earlier showed a point cloud way to do that. This is a volumetric way to do it. But both are providing a lot of structure to the image data. And then the goal is to take that, which will, it's almost guaranteed that will have some noise in it, especially if you treat the entire scroll together, right? There will be erroneous connections and so on. So we need some input of structured information, and then there's some sort of more global step that stitches it all together. And so this is like one of the ways we might get that first information. And then it may turn out that you could input this to essentially the same stitching problem that we currently use point clouds as input for. So those are kind of the two sub problems where we're really up against it.
Exactly. Also, another idea I just had looking at this data. Have you thought about using like different colors for your instances and then like coloring pixels with the instance color you think the sheet has, and then run like a flood fill at the same time on all of those parts?
So you mean like seeding different parts of the unlabeled structure and then growing those out?
Yes, and then at the intersection when two colors touch, you just don't continue to like run for that.
That might be an interesting technique. If someone wanted to do that, that'd be cool. But what I'm just thinking of is that would be a decent amount of development time. And what I'm working on right now is I have a couple checkpoints with the 30 or so cubes that I want to dig into first with the ML and see what that ends up looking like. But that is a good idea.
Yeah, I also want to say thanks again, man, for helping us make these cubes. And if anybody else wants to help us make cubes, it'd be fantastic. Because as everybody can really clearly see now, it's a lot of work and they're high value items. So.
Yeah, James, it's fantastic. Thank you for showing this.
You're welcome. Hopefully we can make a breakthrough somewhere, either intersection or with the.
Yeah, this is really exciting. We have some chat questions we need to catch up on. If anyone, there's a lot more documentation here. So if you are interested in this work that James is showing, check out the awarded prizes page on the website, or send any of us a message. We can point you to it. This is well documented and really exciting stuff. So we have a couple of quick questions. One I can knock out. Can you share more about the new scans, energy level, which scrolls, why these? The answer is no, not yet, but soon. So stand by. Santiago asked how the surface we were looking at earlier compares to scroll 4, so we will get to that momentarily. Tom has asked, when we were looking at some of the crackly patterns in these scrolls, could we not start finding those cracks first with an algorithm and then proceed? The answer is basically, yeah, that's exactly what we would like to do. As it stands, that algorithm is usually a trained one. That's what has worked so far, is taking some instances where we see those cracks or ink-like patterns or regions of interest manually. So where you see them visibly, you label those and then train an algorithm. And then that algorithm can highlight those elsewhere. And of course, the idea is you look at what is highlighted, clean it up a bit, and rinse and repeat. But that's absolutely the goal. So that's sort of the frontier of first letters in these other scrolls, is to do that process. So we're starting to see a little bit of activity there since we doubled those prizes, which is exciting. So keep it coming. Let's see, any other questions? You'll let me know if I've missed something. We do have a few more scroll images we can show. We can get to Santiago's question about scroll 4 if we wish.
We also have Nicola in the chat.
Yes, welcome, Nicola. Thanks for joining us. You just meant to join.
Appreciate it.
Hi.
Ciao, Nicola.
How are you?
Yeah, good. Good to see all you guys.
Yeah, thanks for joining us. Good to have you. Great. I'm going to show for now few more scroll pictures, but anyone can interrupt me at any time. So scroll 3, this will be a bit redundant because some others put some in scroll 3, but this is a photograph. Again, no scale banana, but this one is smaller significantly. It's about half or less the length, and then its diameter is much smaller than the other two scrolls we've looked at so far. So this is what's called a medulla, which means marrow, and it is what is left over after a physical unrolling process that carved away the rest of the scroll. So that's a whole other story, but we don't do that anymore. This scroll is really interesting. So from this view, it looks more or less like the others. If you zoom in, it's a little hard to articulate what exactly is strange about this one, but it just seems to have a lot going on, is what I would say, at the papyrus sheet level. What would you say?
I would say it just looks maybe that it was older to begin with before it was carbonized. So as you might imagine, what happens to a sheet of papyrus.
Yeah, there's lots of waves in the papyrus that are much smaller scale than other scrolls.
It's very intricate, isn't it?
Yeah.
So it's more worn.
It is simultaneously very beautiful and also makes our jobs harder.
Yeah.
But yeah, so this is an image from, I think, Ben, showing just a volumetric segmentation of papyrus and air, and you can see, I mean, the structure here is incredibly intricate. So there's a lot there to work with. I remain quite optimistic, really, that we will solve this, but it's no easy feat.
No.
Here's another view of the same thing. Yeah, if we zoom in on this surface, some interesting features show up. This one has a lot of these cracks that I believe, and please correct me anyone if wrong, these seem to be cracks in the actual papyrus surface, not necessarily cracks in some ink on the surface or something like that. Does that seem consistent with what you all have seen?
Yeah, but they're often intermingled, and so
Yeah. So
what
a lot we don't know.
What I noticed, but I might be wrong, is that the crackle signal in scroll 1 is more has more deramation. In the sense it has more branches, you know. So the fractal structure of these cracks look different. So this is why I'm more prone to say that this is a crack in the papyrus fiber rather than in ink.
Right. Yeah, we're in this position in the timeline right now where we have ink models that work quite well on scroll 1, and there was hope that you could just scan any other scroll and that model would work on that scroll. Now there are differences between CT scans that make that non-trivial, just because of how that works. So you can work around that by doing data augmentation with the intensity values and other things. But kind of the point of showing these images is to illustrate that on top of that, there are also differences within the scrolls. So they're all from the same library, but they span 3 or 4 centuries and were made by different scribes using perhaps slightly different techniques, right? So just because we have a model that works on one, we haven't got the foot in the door quite yet with the other ones. And what we're looking for, like you're saying, is the ink pattern might just look a bit different than the other ones. As soon as the first person finds it, though, this whole thing will blow wide open, right?
Exactly.
And the more of these that we do, you can then start to train models across all of them. So right now, if you train a model on only one scroll, maybe there's no great reason to believe that model will generalize to all of the other scrolls. But as soon as we start having models that have trained on 3 or 4 scrolls, they may very well extend to other scrolls where you can scan a new one and have an ink detection model out of the box that gives you something.
it should generalize at some point.
It has to at some point. Yeah, the question is, how far do we have to go? But
I mean, as far as we know, the papyrus fiber are made of the same material that is basically cardboard, and
Right.
and also the ink composition should not differ that much between scrolls.
exactly. On the one hand, there's a lot of variation between scrolls. On the other, this is very constrained. They're all made of papyrus. They're all written with the same form of ink.
Yeah.
They're all burned by the same volcano.
Exactly. Well, what might change is actually where the scroll were actually
Yeah.
when the the eruption took place, because
And-
some scroll perhaps were in cases, other were more exposed to air. So
And also the age of the scroll when it became permanent.
Absolutely.
And maybe also techniques that were applied during unrolling.
Or how often it was read.
Yeah.
It's just
Yeah.
like-
Yeah, that's true. You think of modern books, a well-worn book has a very different appearance from a new one.
So the
Yeah.
most interesting scrolls are the hardest to read, which is not great for us.
Oh, yeah, that's a logical conclusion.
It's a good point. We also, just the fact that we have this data at all and all of us are working on this and that this exists as a problem is because the people physically unrolling left the most difficult ones for us. So we're grateful they did that, but they did already open all the easy ones.
When
You
we
just
talk
never-
about
Go ahead.
Sorry, when we talk about scroll 3 being older potentially before it was preserved, when you look at that like crackling texture and you say it's probably not ink because it doesn't look like the branching crackles that we see in scroll 1, is it possible that the crackle or that the ink, had 100 years to fade before it was preserved, and maybe the crackle is just much more faint in scroll 3, like by default?
Yeah.
Yes.
Because I would say probably not all of it is ink crackle. Like certainly a lot of it is going to be air gaps and actual cracks in the papyrus, but certainly maybe there are a few faded bits here and there that are ink crackle that might be difficult for us to differentiate.
Absolutely. Yeah, there's so much going on in these scans, and one advantage of having also scanned these fragments where we have ground truth photography of their surfaces is a lot of these features that we look at, like here in this image from inside scroll 3, down in the bottom, there's this feature that I can't tell you what it is, I don't really know. And on the fragments, we also see a lot of things like this, and sometimes they correspond to ink, and sometimes they don't. So short answer is it's pretty complicated, and there's a lot we don't know yet.
Yeah, there's a lot of that thicker mud, quote unquote, on scroll 3 and 4 that it's totally unclear what it is.
Yeah, also like when we trained the machine learning on the fragments, we saw like after 3 fragments, well, the models are going to generalize to other fragments, but that didn't happen for the scrolls. So maybe like if we have 4 scrolls or 3, we see the transfer.
Yeah. Let's show some of scroll 4 to wrap things up. This one's a similar size to scroll 3. It's another midolo. It's like the inside bit. Again, kind of even from this photograph, you can tell this has an interesting character to it. It doesn't quite look like the other ones. Texturally, maybe.
which one is your favorite scroll, Steve?
Well, it's hard to argue with scroll 1 based on what we have right now. Not to have any spoilers, but some of the new data is actually very exciting. My favorite scroll may be yet to come. We will see.
Interesting.
Yeah. Scroll 4, yeah, it's pretty interesting in general, and maybe David can talk about this. It's pretty segmentable. Now this is a view of the very middle, which I have no idea what's going on there.
Which we don't really worry about because maybe title, but in general, they didn't write that close to the middle.
Right. So it's okay that looks like a mess. And it looks like a cool mess though. But yeah, the rest of it, nice separation between layers, and you've been able to segment a lot of this.
Yeah, I think for scroll 4, it's quite separated. The only issue is maybe that they do bend in and out of plane a bit more than scroll 3, whereas scroll 3 doesn't have as much of the bending in and out of plane. It's just micro problems. This one has a few macro problems, but in general, scroll 4 is quite nice.
Do you have any idea? So looking at this sort of zoomed out texture image, there's a lot of what appear to be sort of holes, sort of black spots. Do you have any intuition? Are those actually holes in the surface? Like, is the papyrus surface maybe old and sort of ragged and worn, or is that an artifact of some part of this process that maybe doesn't reflect reality? Or
I think both. There are regions where there is clearly holes as you're segmenting it and you're like jumping across the hole briefly.
just though like a hole punched straight through to the surface?
Yeah, well, not, well, there are some hole punches, but not.
You can see one on the top, yes. On the left side of each wave.
Yeah, I think that has more to do with the end
Okay.
Yes,
What happens at the end of the
each
scroll?
circumference.
Well, one conclusion could be that, I mean, the big ones might be holes, while the small ones, since we are only seeing like a cross section of
It shouldn't
the
be
sheet, could be some fiber that is going more up or down in the Z direction.
So the segmentation just hasn't followed it, and we're
Yeah.
cycling through air.
Yeah, because the general structure is like sheet-like, flat, but there might be these parts of fiber that just go up and down.
Yeah.
And,
I think it would be pretty easy just to pull up the surface volume, and if you pick one hole, you could look at it, know right away whether it was a true hole or just segmentation error or intentional or unintentional based on how the scroll was bending in that spot.
Cool. What's going on here?
well,
We see this also in the outside of scroll 1, and I think in scroll 3 as well.
Yeah, this is an interesting region that I don't think we have any real clear answers on yet. There's a lot of crackle-like texture going on, but it almost blankets this region in a way we wouldn't expect for ink or for text.
there is also a brighter pattern, no?
It is brighter, yeah.
Someone got some ink on their palm as they were writing.
Yeah,
Punched
you
it over the whole
smeared
thing.
it on the surface. Yeah, so this is another example of something about one of these scrolls that we don't know yet. So if you can make sense of it, let us know. This shows up a lot in scroll 4, but not everywhere. Is that accurate? Like there are places that are more relaxed.
Yeah.
There, I've just zoomed in more to some of that pattern.
Yeah, the thicker mud, what is it?
Right, is this some artifact of the eruption? Is it something that was on the scroll pre-eruption? We don't know. Looks cool, but love for it to
Like, is it,
translate to us recovering some text.
we're told it's not possible that it's part of the Oswald method, but no, that hasn't really been verified.
Right, yeah, the scroll was subject to a physical unrolling process that involved chemicals, basically.
Possibly more than one technique. 'Cause
Yeah, I don't know, but it seems the possibilities window here is pretty wide. So, please help. I think that's it. Let me see if I have any more images. Nope, that's all. So
there are
let's
some questions too.
check the questions and then we'll wrap things up because we've had a nice hour here.
Yeah.
Maybe we can talk a little
Yeah.
bit about what we're up to with good resources for the community.
Yeah, I would like to give a short preview, like very short, of
Okay.
what we're building. So basically, let me share my screen.
While you do that, someone asked, is this from scroll 4, which segment? Well, we were just looking at that. It is from scroll 4. Does anyone know off the top of their head which segment? I'm the one who made the slide and I don't remember which segment, but I could go find out.
One of three. There's three big.
That's true. So there are only 3 segments.
Yeah.
And in the view, I'll share real quick again.
I will.
So you can
Stop
take a
share.
look at all 3 of the scroll 4 segments. One of them will look like this, and this region, the bright region in the middle is what we're looking at. And, oh, thank you. I'll share my screen. This is the segment from scroll 3, zoomed out. Yeah, as David was saying, this is one of only 3 such segments. One of them looks like this, and that bright region in the middle. This is what we're looking at.
Scroll 4,
Scroll 4.
scroll 4.
It is scroll 4. Did I just say
Yeah.
scroll 3? Scroll 4, thank you.
Scroll 3 has not been segmented top to bottom.
Correct. Yeah, shoot us a message if you want help finding it, but it should be pretty doable.
So getting back to that, many people in this room approach this problem. I mean, we're not working on the problem from the beginning, Steven. So one of the highest difficulty we found was actually accessing the data. And we realized that to get more contribution, it is necessary to have something to download and access the data in an easier way. So we are developing, now it's almost finished, but a Python library that would allow want to just, for instance, here you can see from Vesuvius import volume, and then you instantiate a volume object where you specify that you want to scroll. For instance, here is scroll 1, scanned at 54 kiloelectron volt, and with resolution of 7.91 micron. That is the canonical scan we are using. And here we are not downloading the data yet, but whenever we access to the object, to this object with some slices or some index, just like an NumPy object, we are downloading the data that we need. So basically, to access the scroll data, but this will also work for the segments, and also will work for the cubes with another class. We won't need to download everything every time. If we want to test simple stuff, or we want just to do a quick visualization, we don't need to download a volume, then delete it and download another one, because we know that not everyone has terabytes of SSD to dedicate to this problem. So I think this will greatly help people onboarding, and then maybe later, if they want, they can dedicate more resources to the problem. So.
Yeah, and also you can specify how much storage space you want to have for cache, so that you don't have to download it every time. And yeah, only the parts that you're interested in.
Yeah, I'm really excited about this.
And also, if we talk a little bit about the data format here. So the scans are huge volumes, a lot of data. So we tried to make this a little better and have less data for each scroll, but still capture everything that we need to have. So yeah, this is also a compressed kind of volume as a new standard format.
This is awesome.
Thank you.
I love it. I think we'll hit some questions and wrap things up. How does that sound?
Yep. There's a question about which volume we're using this scroll 3 to work in VC and Tomato.
Me?
Yeah.
I use the 3 micrometer volume downsampled to 8 micrometers.
You've done the downsampling yourself?
Yes.
Okay.
And in VC, we're using the 7.9 resolution. Is there only one up? I'm assuming it's 54 electron volts, but if there's not a 54, whichever one is 8 microns.
There is a 53 kiloelectron volt 3 micron. There's a 53 7 micron.
Okay,
and the last one is 73 micron.
Okay.
There are 2 3 micron scans.
Yeah.
You know which one you're using?
53.
Cool.
Yeah, in VC we use the lower resolution just because the 7.9 resolution, because the 3.24 is just the error of running OFS through the higher resolution just propagates too quickly. So it helps to have less information for OFS.
Yeah. Here's last question. Speaking of titles, do the papyrologists think that the title area has already been segmented in scroll 1? And I'll pull up maybe the image that shows this and discuss that. Okay, so here's the region of scroll 1. This shows the dark gray in the background is the expected full extent of the scroll in unrolled form. And over on the left, you see these segments where we have text, and in fact, we have the end of the text in that partial column there, right here. And yes, we're hunting for the title somewhere in here. The question is, do the papyrologists think we've already segmented where it is, or might it be in one of these yet unsegmented areas? The short answer is there's no certainty behind this, so we have some theories. You've talked with them some. What do you think?
It's all probabilities, and there's still definitely areas of high probability that haven't been segmented, particularly in the center region.
Like here?
Yeah, and to the right. Like it's either going to be underneath the final partial column, somewhere in there, or it's going to be in the middle in the empty column, are the highest probability areas.
Like over here?
Yeah. But it's very hard to segment. So, and ink detection may change in an area that compressed. And so there's a bunch of different variables there.
Yeah, and what we've segmented so far is kind of a combined product of where it's possible to do segmentation and where we most expected the title. But the title could be anywhere in here, and a lot of these regions are quite difficult currently. Yes, Luke?
I have a question. So according to the papyrologist, is the ending coherent? Like, does it stop in the middle of a word or something?
This ending?
Yeah, like, is that like a full sentence or something?
I have not ever heard otherwise yet. Yeah, to my knowledge, this is.
And the little mark there
This is not ended.
Is that indicates something?
Yeah, this marking here, which is not a letter, does also indicate something. Yeah,
Something.
so it's a coherent scroll ending.
Gotcha, thank you.
And I think that the actual contents of the text, when read and translated, also align with that. You know,
Yeah.
It's a sort of concluding remark type of statement.
Yeah, very cool.
It's worth noting that our understanding of exactly where the middle is isn't 100% because we don't know how far the text continues that was burnt off at the top.
That's true. So this scroll, we have what appears to be the bottom of the scroll. Let me show this again. So David is saying the top here is where the scroll is like physically sheared or somehow harmed. I mean, it looks like part of the top of the scroll is missing, and we know that's true because the text is cut off. At the bottom, we haven't gotten there yet, but it looks like when you look at a photograph of the scroll, that we have it in sort of intact. So here's that. So this is the top in the top right, where you can see it looks quite damaged. It's cool because you get this really nice view into the structure of the scroll. The bottom end is flat and looks much more like it contains the full extent of the scroll. So yes, we don't know how much was lost at the top.
And our scan might be a millimeter or two short of the very bottom of the scroll.
Yes.
As well, which isn't a huge deal.
But that's okay.
Yeah.
There should be a margin down there that
It's not a big margin, we're sure of that, right?
the margin between text and bottom of papyrus.
Oh, no, does the scan go all the way past the end of the scroll, both ends of the scroll?
That I don't know off the top of my head. I do recall it being small, but I couldn't.
Okay.
I won't make up a wrong number. But
Okay,
yeah, I think we effectively we had it.
okay.
Great. Anything else? We might. Yeah, I think this has been great. Thank you all so much for joining us. Any concluding remarks?
Thank you.
Yes, thank you all so much. We're also excited to get to work on this, and this community is amazing. We're really excited to start getting letters from these other scrolls. We're working on stuff we're really excited to share with you. And thanks for everyone who joined us today. We'll talk to you all soon.